So we're also going to include in this chapter some information about vectors because oftentimes in calculus or in Calc 2, we will be looking at vectors um, as parametric equations as well. So they kind of go hand in hand. Now, a lot of this, if you've had physics, a lot of this is probably review, and you may have worked with it more than I have, to be honest. So, okay, so we're just going to get into it. So this may or may not be an easy day. We have lots of vocab today. So a vector is an ordered pair representing both magnitude and direction. Magnitude means length of a vector, and direction is going to refer to an angle. We'll get more into those details in a minute. So we're used to writing ordered pairs like this. The ordered pair AB would just represent this single point right here. And so what's new in this chapter is that we're drawing a directional arrow or array from a starting point to that final point. In this case, it's from the origin to the point AB. And so we change the notation instead of parentheses to be these little like brackets. So that represents the directed line segment from the origin to AB. A few vocab words here. We call the ordered pair 0, 0, which is where that ray starts. That's called the tail. And then the ordered pair AB would be called the head. So you have like a head and a tail. And we also call A and B components. So sometimes in the homework tonight, you'll be asked to find the component form of the vector, and that just means figure out what A and B are. The direction angle. The direction angle of a non-zero vector is the smallest non-negative angle theta formed with the positive x-axis as its initial ray, and then you've got a terminal ray as well. So that's important because you'll want to know, which direction you're rotating basically for that angle. All right, the length of the arrow represents the magnitude. So I kind of referred to that at the top of the page. When we say find the magnitude, we mean find the length. What is the distance between that point AB and between the head and the tail, basically? Some notation for finding magnitude is usually putting like an absolute value symbol around, let's just call this vector V, something like that. Or you'll see if your vector is not named something, like if it's not called vector V, it'll look like an absolute value symbol around the component form itself. And the formula for this is nice and simple. It's just the distance formula because you're finding the distance between 2 points, or Pythagorean theorem, however you want to think of it. It's a square root of a squared plus b squared. That will be the magnitude. So magnitude should just always be a number. Any two arrows with the same length pointing in the same direction, so same angle, represent the same vector. So these two vectors are equivalent because they have the same length and they have the same angle. You could transform, you could shift this vector to the right and down, and you're going to land on this vector. So basically 3, 4, this vector right here is in its standard position. And the other vector is just if you were to shift this, up 1 and left 4, you would land on the other vector. So that's all that those two are. The 0 vector would be 0, 0, or the origin. The unit vector means a vector that is 1 unit in length. You'll see the two different notations there. Even though we have this new notation for vectors, we could still use ordered pair notation. So either notation may be used. And you might also see some other notations. So other notation. Sometimes we will see maybe they'll call a vector V. And so vector V could be labeled like that, like V with a little sort of half arrow on top, or it could be bold. they'll write it in bold. Writing in bold is kind of hard to hear, but so like a bold letter could represent a vector as well. So either way, there's lots of different little ways to denote a vector. If an arrow has an initial point x1, y1 and a terminal point x2, y2, so initial point is the tail and its terminal point is the head, it represents the vector x2 minus x1, y2 minus y1. Order does matter here. It has to be head minus tail for the new vector. And that's for both components. We can combine vectors, we can scale them. So like geometrically, what does scaling a vector look like? If this is vector u, then vector 2u has the same direction, just double the length. Vector negative u is just going in the opposite direction, opposite, pointing in the opposite direction, but still at the same angle there. Excuse me, and half would be half the length. And if you add two vectors together, so if I want to do vector u plus vector v, you use this head to tail rule where you say attach the tail of the second vector to the head of this one, and then your resulting vector from the tail of the first one to the head of the final position, that vector is u plus v. Another way to look at that, if they don't do the head to tail for you, if they say here's vector u, here's vector v, if they share that same initial tail point, then you just have to bring this up here, kind of sketch it in at the same angle and figure out still what that u plus v vector would be. So again, for those of you in physics, you've probably worked with vectors more than I have, but we do use them in calculus in order to help us model motion of objects that are moving in a coordinate plane. So that brings us back to our particles moving along curved paths in a plane. When we're talking about motion of objects, this goes back to the beginning of the year. This is the same as what we did before, slightly different on what we call position. So if you remember in the beginning of the year, the position function was always s of t. Here, it's usually r of t when we're talking about parametrics. So not a big change. And then velocity is usually denoted by v of t. That's the same as it was before. And remember, the velocity vector or the velocity equation, whatever it will be, is going to be the derivative of the position. And we'll also be looking at acceleration, which is still a of t. Remember, that's the derivative of the velocity. It's also the second derivative of the position. There is one extra thing to put in here, speed. You'll often be asked to find the velocity and the speed. If you have the velocity vector, so if you have that the velocity vector v of t is equal to some a b, you have that value, then the speed is the magnitude of the velocity. In other words, it's equal to the square root of a squared plus b squared. So you'll often be asked for velocity and speed, and the thing that people tend to mess up is they give speed as the answer to velocity. Velocity is a vector. Speed is the length of the vector. Some differentiality rule, I can't say that word right now, differentiability rules change. We might have vertical tangents. We might fail the horizontal line test. We've already looked at parametric curves that cross themselves that aren't actually functions at all. So all of that is okay. The only thing that would make a curve not differentiable, because all of these things would have caused us to, or some of these things would have caused us to not be differentiable. The one thing that we can't have still are cusps or sharp turns. So differentiable if the curve is smooth, if the parametric curve, let's say that. The parametric curve is smooth, it's differentiable, meaning it has a derivative. But if it's not smooth, then, not smooth is like having cusps, something like that, or having a sharp turn in general. All right, let's do some practice examples. So find the magnitude and the direction angle of the vector -1 square root of 3. I'm not sure what that v is doing up there. So magnitude, using our notation, that's the magnitude of, oh, maybe that's what it was. I wanted to call that v, so I could just use that notation. The magnitude of v is the square root of -1 squared plus radical 3 squared. So its magnitude is 1 plus 3, square root of 4 is 2. Magnitude is 2. What about the direction? If it helps you, you could sketch the angle. I think it's helpful. Plot the point -1, radical 3. It would be over here in quadrant 2 somewhere, right? Something like that. Remember, the direction angle is the positive, the smallest positive angle between the positive x-axis and the terminal side. So that's theta. We're looking for a quadrant 2 angle. We do know that there's this little right triangle formed, right? It's got a -1, a radical 3. So if I'm trying to find that theta, I can use its reference angle and say the tangent of theta should equal negative radical 3. And so what is the quadrant 2 answer for that angle? So if we're talking about radians, this is the 60-degree angle, right? So it's 2 pi over 3. Or if we're talking in degrees, which we usually are with vectors, that's 120 degrees. Same thing. Find the component form of a vector with magnitude 3 and direction angle 40. So again, it might help to sketch this. Sketch a 40-degree angle. And when we say that we have a magnitude of 3, that's the length of that vector. So we need component form. Component form means figure out A and B. In other words, if this were a right triangle, A would be the adjacent leg and B would be the vertical leg. So I can use sine and cosine for that, right? I could say to find A, I could say cosine of 40 degrees is equal to A over 3. So whatever 3 cosine of 40 degrees is. And sine of 40 degrees will equal B over 3. So we can solve that for B. And so component form will give me, I gotta switch to degree mode. Oh, I don't have my calculator out. Once I get my calculator out, I'm gonna switch to degree mode and type those in to approximate. While we're waiting for that to fire up, we can use our more general rule. If you're given a magnitude and a direction angle, then A will always be R. I'm going to call R the magnitude. It will be R times the cosine of theta, and B will be R times the sine of theta. It should always work out like that. Okay, here we go. So change mode to degree mode. And then what did we say? 3 cosine of 40 and 3 sine of 40. So 2.298 about. And 1.298. All right, draw a picture to represent 2, 3 and find its magnitude and direction. Okay, draw the picture. So you're plotting the point 2, 3 just like you normally would, and then drawing a vector. Make sure you put the arrow in there and label it 2, 3. Find its magnitude and direction. Well, its magnitude, we'll use this notation, the magnitude of 2, 3 is equal to the square root of 2 squared plus 3 squared, square root of 13. Remember, it's like that because you're just saying, what is the distance between the point 2, 3 and 0, 0? You're just doing Pythagorean theorem there. The directional arrow You don't have to use sine and cosine. I mean, I do have a radical 13, which is nice, but you can use the components too, right? That's 2 and that's 3, and the theta we're looking at is inside of the triangle now because it's in quadrant 1. So I would just use tangent. Tangent of theta is equal to 3 over 2. So I'll keep this in degree mode. Let's see. 3 over 2. Second tangent of 3 over 2, about 56.310 degrees. All right, example 4. Let u equal this and v equal this. Find 2u plus 3v. So I would just write what 2u is going to be. Multiply that by 2. That's negative 2, 6. And add to that 3v. So that's going to be 12, 21. Add those together. So you just add the like components together. So this is going to be 10, 27. For part B, u minus v. I'm not going to show the work on that because I don't have anything to scale up. So just subtracting negative 1 minus 4 is negative 5. And 3 minus 7 is negative 4. All right, and then part C, this means magnitude. It's easy to read it as absolute value, but we're talking about magnitude of 1/2 u. So let's write out what 1/2 u is. That'd be negative 1/2 3/2. And then the magnitude of 1/2 u is equal to the square root of 1/4 plus 9/4. Square root of 10/4 is square root of 10 over 2. There's the magnitude. We might get some word problems. So this is where we have to think a little bit, be careful of these bearing angles. An airplane flying due east at 500 miles per hour in still air encounters a 70 mile per hour tailwind acting in the direction of 60 degrees north of east. The airplane holds its compass directly east, but because of the wind, acquires a new ground speed and direction. Where are they? So, okay, so what do we have going on? I like to always see things happening around the origin to help orient myself. So the plane is due east at a velocity of 500 miles per hour. So we can call that a velocity vector. And so I'll call this, let's label that, that's P. And then we have north of east. So if you have a tailwind acting in the direction north of east, you're looking east and going north of that 60 degrees. Okay, so that's like that. And that little guy is 70 miles per hour. We'll call that wind, W. So this tailwind that's pushing up on it, it should veer our plane off course a bit, right? Headed a little bit north. And so compared to where it was, and it since it's a tailwind, it should be pushing it a bit farther. So this asks, what's the new ground speed and what's the new direction? They're not headed due east anymore. What's the new direction? So let's write some things out. Let's figure out what our vectors are for the plane. For the plane, I can see this without doing any math. It has an x component or an a component of 500 and a vertical component of 0. The wind is going to take a little more work because we have an angle and a magnitude. So remember how that worked before? When you have an angle and a magnitude, you're saying, well, the horizontal component will be 70 times the cosine of 60 degrees, and the vertical component will be 70 times the sine of 60 degrees. And I'm just going to leave those in that form for now. And so what we're looking at is what is, since it's a tailwind, what is the P plus W vector? All right, so that would be 500 plus 70 cosine 60, and then 0 plus, so just 70 sine 60. I need that vector I need that new velocity vector so that I can figure out the ground speed. Remember, speed is just magnitude. Speed is magnitude of P plus W. Now, it would be the square root of this squared plus this squared. I'm just going to type it into my calculator because I don't want to write it all out and type it all in. So I'm in degree mode. I'm just double checking that. It's the square root of 5. I could put this, I was just contemplating. I could put these in y equals, but it's fine. 500 plus 70 cosine of 60. That gets squared plus 70 sine of 60. That gets squared. So the magnitude is 538.424. And we're talking about a velocity vector. So this is still a speed, right? So this, not a velocity vector, I'm sorry. We're talking about the magnitude of the velocity vector. So this is still miles per hour. All right, so we have that. What about the new direction? So you went from, facing 0 degrees to having a 60-degree act on you, basically. So what we're just looking at is, okay, if this is our P plus W component vector, I could say from here, the angle formed would still be in the first quadrant. Tangent of theta would equal the y component over the x component, right? So it's going to be 70 sine of 60 over 500 plus 70 cosine of 60. So theta is about equal to something. I'm going to do the work first. What was it? Sorry, 70 sine of 60. I guess I could probably save myself typing by just putting in radical 3 over 2, but that's fine. Divided by 500 plus 70 cosine of 60, because that's just a half. Second tangent of that answer is about 6.465. 6.465 degrees. Now we need a bearing on that. So they gave us a bearing of north of east. And since we're talking about a little angle that opens up in this direction, we're saying this is P plus, that's P plus W, and that's the vector. That is east of north. All right. On to example 6. A particle moves in the plane so that its position at any time greater than or equal to 0 is given by this. So that's a vector. It's the position vector. That's R. Find the velocity and acceleration vectors and describe the position and motion at time 3. Okay, so the velocity, v of t, will be, I'm just taking derivatives here, and I can use either notation. So the velocity will be 3 cosine of 3t, negative 5 sine of 5t. And we're supposed to find v of 3, so I just will right here. Actually, well, no, yeah, I will. So v of 3 is 3 cosine of 9, negative 5 sine of 15. I'm squeezing it in there. Those are not degrees, so I'll have to switch back to radian mode. And then a of t would be negative 9 sine of 3t, negative 25 cosine of 5t. And describe position and motion at time 3. So motion would be velocity. So based on the velocity, I can see that the particle is moving to the right. And because that's negative, down. And then what about the position? So r of 3 is equal to sine of 9 cosine of 15. There's not really anything else to say about that, just that's the position, and at that time it's moving to the right and down at the same time. Okay, a particle moves in an elliptical path so that its position at any time greater than 0 is given by this. Find the velocity and acceleration vectors, then the velocity and acceleration and speed at pi over 4. So velocity vector is 4 cosine t and negative 2 sine t. And acceleration vector is negative 4 sine t, negative 2 cosine t. Velocity at pi over 4. Let's see. Radical 2 over 2 times 4 is just 2 radical 2. Negative 2 times radical 2 over 2 is negative radical 2. And the acceleration at pi over 4 is negative 2 radical 2, negative radical 2. So it doesn't ask me this, but the particle is moving to the right and down, and its velocity is decreasing in the x direction because that's negative, and it's decreasing in the y direction. I could also talk about the speed. Remember this. When velocity and acceleration are opposite signs, it's slowing down in the horizontal direction, but it's speeding up in the vertical direction. And then speaking of speed, it's the absolute value, or sorry, not absolute value, it's the magnitude of 2 radical 2 negative radical 2. That is the square root of 2 radical 2 squared is 4 times 2 is 8, plus 2 is the square root of 10. Sketch the path of the particle and show the velocity vector at the point 40. It tells us it's an elliptical path. So I know I've got an ellipse. To sketch the path, I might say, let's just start at t equals 0. What's the position at 0? 4 times sine of 0 is 0, and 2 times cosine of 0 is 2. So the first position is 2 right here, t equals 0. And then to figure out which direction it's headed, maybe I look at pi over 4, for example. When you plug in pi over 4 to the position function, you get 2 radical 2 and radical 2. Those are positive components. That would be over here somewhere in quadrant 1, right? So that tells me that this ellipse, I know it's an ellipse, so I know it's got these 2 vertical points, but I also know that it heads around in this direction. So in interest of length of the video, you can find some more points. This is t equals, I believe this is pi over 2. And you'll be at the point 40. So, but it's an ellipse. So to draw directional arrows, I can just say, yeah, it rotates this way. All right. That's it for today. So tonight's homework is this vector supplement worksheet. And we're just doing 1 through 35 odd. So just lots of little problems to practice. And if you don't feel like you need tons of practice on the magnitude stuff, I just want to make sure that you know how to find speed. That's a common AP question. And make sure you do the word problems. I think those are important to get the hang of. All right, that's it for today.